Okay, so welcome everybody. So today it's part 2 of crushing the database system's interfaces. And last time we talked about, okay, what about the return type of a query? What if the SQL statement returned a subdatabase? And I motivated that with the existing problem of SQL, that SQL is not only a query language, but also a transformation language. So whatever you do at the end of the day, SQL will return a single table. And that may be in the way. And it has a couple of problems. It creates duplicates, it loses schema information, loses information about keys and stuff like that. So many things are lost on the way. And we looked at different ways how to handle these situations. So I'm not going to repeat all of that. But basically, we looked at white box and black box methods. So black box means, okay, you do not touch the existing database management system, and the white box approaches, you integrate it somehow into a source code. And those are very common design principles in a way. So whenever you're in a situation you want to extend your database management system or whatever system, you want to extend it, you first think about, can I do this stuff just by wrapping the existing system without fiddling with the source code? Because that's the easiest to do, and that is something that works even if you don't have access to the source code. So that's the first thing I would always think about. And then once you did that, you can always go one step further and see, okay, maybe that's not the best, maybe I have some performance issues. What if I really integrated that into my system? And that's what we see on the right side here. When you really integrate it, that's this part, into the source code. But we started on the left, and then we looked at different rewrite methods. So the very trivial ones are really okay. If you want to have a separate result table for each participating results, you basically can run a separate statement that runs a query, the original join query, joining these three relations, and then projects the results back to the attributes of P, including the ID. That basically gives you the tuples that take part from P. And you do that for each and every relation that participates in the query. And of course, you wrap that in a transaction to have a snapshot property. Because in theory, if you don't, what happens if you don't use a transaction here? If I omitted the begin transaction and commit, what could happen? Yeah? Yes, exactly. Between executing these queries, the data could change. So it could be that the second statement sees a different result than the first and stuff like that. So of course, each statement, each select statement is a mini transaction in itself. So it operates on a particular snapshot. But in between any of these two statements, in between here, or here, some other transaction, some other operation might change the state of the database, and then would see very, very weird results. Okay, and then we looked into a couple of rewrite methods. So this is a hack in a way. The idea here is that I materialize the output of the original single table result into a separate table. That's also called a materialized view, not to be confused with a standard view. If you write create view without the materialized, no query is going to be executed in the database system. It's just an alias in the system. But if you write materialized view, and some systems support that, the result is actually materialized, and then all you have to do, same as before, but you select from that materialized view rather than writing, having to execute the query again. That's one way how you could simulate that. Then we looked at other ways through subqueries, basically saying, okay, I want to have all of those tuples from P where the ID is in the remainder of the join result. So this subquery is always G joined L. And then I just check whether the P ID is in that set, and that gives me the same semantics in this case. And you can also do that materialized. Okay, so and then we started looking into the white box approaches. In particular, we started with acyclic query graphs. So query graph meaning, okay, you have for each participating relation, you have a node here, we have 4 relations here, each edge meaning, okay, there's a join condition, there's a join condition, there's a join condition, and then the question is how to execute this stuff. And leads to one thing that you see is, okay, how do I even transfer that into a tree. Yeah? So we want to transfer that to a tree in order to be able an algorithm that's called the Yannakakis algorithm, aka the Phil Bernstein algorithm, but in literature it's called the Yannakakis algorithm. And basically, when you have an acyclic query graph, you can easily regard that as a tree by just picking a random node. You pick a random node from the graph, and that's what I'm doing on the right here. So yeah, here, if I pick R, that is a tree I get. If I pick S, that is a tree I get. Except here, the order, I have two different orders. So whenever a node has more than one child, yeah, you can always create a different tree like that and recursively. Yeah? So that's a huge number of trees you generate. For that, actually here it's 12 possible trees just for this simple graph. Yeah, and then what we do is, and this is the actual Yannakakis algorithm, and that's where we ended up with last time, you perform a semi-join reduction. And we first do a bottom-up step on the tree, and then we do a top-down step. Again, the blue stuff is a fill grade here, and what I do is, what I will be using is semi-join, I don't know. I think both pronunciations are used, not sure. It's a bad name, kind of, because it's more like a filter operation. So a standard filter operation, a standard selection, you have a predicate, you say where A equals 42 or something like that. This is the same spirit. So this is basically filtering R. This is saying, okay, if I joined R with S, which tuples would participate in that join? That is what the semi-join is answering. Yeah? So you get the same result when you join R with S and project back to R dot star. And this works in particular because relational algebra is duplicate-free in contrast to SQL. Yeah? In the statements before, I always wrote distinct. Yeah? When I had these rewrites here, I always wrote distinct to make sure that I don't receive any duplicates. You have to do that in SQL because SQL is not duplicate-free. Tables are not duplicate-free in SQL, so you always have to be careful. It's a slightly different semantics, which allows you to shoot yourself in the foot at times. Yeah? So here, in relational algebra, I don't have to do this, because I get duplicate removal for free. Okay, so with that, now I do a bottom-up part. So I first do a semi-join of T with U. Again, I filter T. I will remove those tuples from T that are not part in a join with U. Yeah, I only want to have those tuples from T, the subset of tuples from T, that actually form a join result of some sort when joined with U. Yeah, that's what I'm doing here. I could also start with this one. Yeah, that's again the ordering problem. Yeah, we will look at that if you remember cost-based optimization from the undergrad lecture or for some other lecture. If I hard code to say it's always on the left, that's a bad choice, and I might miss the optimal plan here. So it's an enumeration problem I'm having here. Huh? But for the sake of explaining the core idea, that's good enough. So, okay, so I do a semi-join here. Now T will be reduced to T prime. Yeah? So some tuples from T get removed. Now I continue and join with S already on the reduced T prime because what I know is, I don't have to use T anymore. I can already operate on T prime, which was reduced before. So I further reduce T prime to T prime prime using S. And you could also regard that as the information which tuples participate in the join should be propagated all over the tree. And that's what I'm doing here. The propagation is, the information is propagated bottom up to the root. Yeah, and that has some implications for the root node, for the root relation. And then I propagate the information down again. I do that once up and down, and then nothing can happen anymore. It's guaranteed that everybody knows about every other join result. So I reduce this further, and now I go up in the next step. Now I reduce R using T prime. That happens here. Now R gets reduced to R prime. Okay, that information I better propagate down again. That happens now in the top-down step. Now I create another T prime prime prime, which reduces T prime prime further. and then I propagate the information to U, creating a U prime, and to S, creating an S prime, and then I'm done. Now all of these results correspond what I want to have in this kind of result. All the tuples were reduced to only those ones, to the subset that take part in the actual query. Everybody, all the other tuples could be neglected, could be discarded. What would that mean for standard query processing? And if I don't want to have a result to be, if I just want to have the single table query anyway, does that help me in any way, knowing about this algorithm? Where's the other glasses? Someone an idea? So I reduce the 4 tables that, I mean, in the standard query, if I do the single table join, okay, I do some processing on those 4 tables, on the original tables. But I didn't do this. In this Yannakakis algorithm, I first reduce the relations, and then I do some magic. Then actually here I'm done already, but for the single table result, yeah? Because we have less data then? Yes, excellent, yeah, because we have less data. So before starting standard query processing, I reduce the input data sets, and now I have a choice. I can basically return these results as is, that's my result database, or I could say, okay, those reduced relations I use as inputs for the single table query result. Yeah, and then I have less data to consume during query processing. That's actually a valid approach, and we will look at that in separate notebooks, because in particular for distributed database systems that plays a major role. This is what you're seeing here is a more general version. Huh? Okay, very good. So I can make this bigger, right? So that's the overall result, right? And that's where we stopped last time, if I recall this directly. And now we look a little bit at cyclic query graphs, something like that on the left. And to handle that, handling this is relatively easy because the idea is we will transform the cyclic graph into an acyclic graph with a number of steps. Yeah, that's the trick here. And after we transform it until we end up with an acyclic graph. And once we have the acyclic graph, we can run the Yannakakis algorithm again. Yeah, so that's the algorithm I will be presenting. So if you have a graph like that, which is obviously cyclic, what I do is I will join some of the nodes. Yeah, so here, for instance, I'm joining T and U. Those two, I'm folding them together. I'm folding them into a view, if you want. I'm folding them to say this node now represents the join result of T and U. And I represent that as a separate node in my graph. And when I do it like that, I end up with a graph like this. Yeah, now I have the join result of T and U. And you don't have to materialize that at this point. It's just conceptually, yeah, arguing along the lines of joins. Yeah? And then, of course, you have these 2 edges. Oops. I have these 2 edges here. Yeah. That doesn't help if I make it red. Yeah, I have these 2 edges here. Yeah, this red edge and the green edge. Yeah, this pointed to T, this to U, so there are now both conditions between those 2 nodes. Okay, it's still cyclic. Then I perform another join. Now I'm joining R with S to form this new node, R joined S, and hey, that's an acyclic graph. And this you can feed into the Yannakakis algorithm again. That's basically the algorithm. Huh? And yeah, this is one folding order. Of course, there are many folding orders. You could also do something like that. For instance, if you start with this graph on the left, you could also say, now I join T and S, those 2 nodes. And then I end up with a graph like that. In a single step, that's already acyclic. Nothing left to do. Put it into Yannakakis, good to go. Yeah? That's basically the algorithm. And why can you do that? Well, the intuition is that inner joins are associative. Yeah? So whether you write something like this or like that, That's basically what join order is about. Yeah? So this associativity basically is, that's the reason why we can do join order, because here I first join R with S and then the result with T. Or alternatively, S with T and then the result with R. But that gives the same join result overall. It doesn't matter in which order I do this stuff. Yeah? And that's what I exploit here, because basically these brackets I have here, the bracket here is a node in a way. Yeah? That's kind of the node, the bracket saying, okay, I first join R with S, and whatever the result of that is, I join with T. Yeah? It's basically another way of forming brackets into your join graph. Yeah? Versus, this bracket here, that's basically this node. Yeah? So and then again, after you're joining S with T, you join it with R. Yeah? Versus, this means there's no brackets defined. Yeah? Here in such a graph, you don't say whether you first join R with S, S with T, R with T, or whatever. Yeah? And that's very similar to, so it follows that any join of a relation X with relation Y leaves the join result of a query graph unchanged. And that's the idea we're exploiting here. And there's an analogy to standard query processing. This is similar to following a join order in a single table query plan. Every single join folds the two nodes into a view. This means smaller query graph on base relations and intermediate views. Again, we can actually reuse the same slide here because the slide has, if you look at it, has nothing to do with ResultDB. If you have a standard single table query join, like the one here, yeah, you have a join on R and S and T with those conditions, and you want to compute a single table result. So what do? You pick a join order. And picking a join order actually means you pick an edge from the graph. You say, this is the edge I'm now looking at. Yeah, so here you're looking at I know I'm going to pick this edge. Yeah, if I pick this edge, I end up with this in the middle. Yeah? If alternatively, I picked this edge, yeah, I would end up with something like that. Yeah, so basically what you do in query optimization, in the undergrad query optimization we looked at, you fold the graph one by one to eventually have a big node, one single node representing your entire join result. Yeah, representing the entire expression with brackets here on top. Yeah? That's all what's happening in join enumeration. You know? And of course, I mean, there's a lot of research going on. I mean, research is a big part of research, and also what we do in our group is always questioning assumptions. Yeah? Not only interfaces we're questioning, but also algorithms, or things you don't see anymore because you take them for granted, because some professor or some textbook says it has to be like that. What are the assumptions you might see here in this slide? Does anyone an idea what I might be talking about? Something that is a constraint, or it's defined to be, it has to be like that, it always was like that, we are not going to change it, right? You see that also every day. Well, why would we change it? We always did it like that, was successful, why would we change it? Someone an idea? Maybe that you can only ever join two related at once. Excellent, yes. That's a hard constraint. It actually makes it easy to put that into a graph. Yeah, because the edge is between two nodes. And that is what will be translated into a join, either in relational algebra or into some sort of physical execution plan. Yeah, this is our problem. This is our problem bear, so to say. It's saying, okay, whatever I do, I can only join two relations, which is completely stupid. It's a completely stupid constraint. It was already violated in the 90s in data warehousing. I think we had an example when we looked at cross-product joins, whether it makes sense or not. Yeah? It's a constraint, yeah? And it actually leads to the join enumeration problem, Because if I have that constraint that I can only join two relations at a time, yeah, I have to come up with join enumeration algorithms that take binary joins and try to come up with binary orders and enumerate the entire search space or make some compromises, are greedy or whatnot. Yeah? But if I relax that condition to say, okay, maybe I allow for joins that take more than two inputs, how would I scribble that in the graph? Yeah, I mean, if you make it, maybe make it a new slide somehow. I scribbled it here. So I have a graph with my three relations. So if an edge here, like in this representation, represents a binary join, how would I represent a ternary join, like a join operation joining all of these relations at the same time? Graphically, how would I do that? Yeah. A dot? Oh, very creative, pretty cool. So actually a little bit like an entity relationship modeling, yeah. You could say something like join, use entity, something like that. It's a ternary relationship in a way, like in ERM. Why not? Cool, yeah. Some other ideas? It works, absolutely works, I agree. I mean, in ERM, you would actually, you have entity type relations and join. Let's not go into that rabbit hole. Other ideas, huh? Yeah, I could draw a circle. Yeah, that's right. So kind of saying here, that's my new view, my new super node in a way, if you want it. Yeah, and then maybe I make a comma in between those to say that's a list of nodes where I don't define an order. I don't define how I join R, S, and T together. I'm just saying it somehow happens all at the same time. Yeah. Some other idea? I mean, the standard graph doesn't allow you to do that. The standard graph has these edges connecting two nodes. But there's an extended definition of graphs. It's called hypergraphs. Hypergraph means, I'll write it down, hypergraph. And in a hypergraph, you can have edges that connect more than two nodes. Don't ask me how to draw that. I have no idea. Yeah? You can make a whatever. You can make a circle. You can say, okay, this is my edge in a way. Yeah? Or you could say, maybe let's add another relation, meaning these three relations here are connected by an hyper edge. This U is not connected, and then these three are connected by a hyper edge and stuff like that. Yeah? So you can do these kind of things. Yeah? So notation is not on the way, and there are extensions arguing along hypergraphs. So. Yeah, okay, but we started again. I mean, it's not only in research, but it's always great to know, okay, what the heck, I'm working with these methods, and someone told me that they are constrained to do this, or that they have to follow this constraint. Always question, ask back, why the heck do you want to have it like that? Who invented that? What's the motivation behind that? Yeah? And in databases, there are many, many places where you can question existing assumptions. Yeah? The problem is that when you are in the field, you're sometimes blindfolded and don't see it anymore. Yeah? Okay. Yeah. Okay, so that's the overall algorithm. Yeah? So basically, that's what I explained. So the first step is making this graph acyclic. That's what we do in phase one. Yeah. So while our query graph has cyclets, we have to pick a node X on a cycle. And that leads to the tree-folding enumeration problem. You can pick those nodes blindly, but there are better ways of doing that. We actually do research in my group that does it more efficiently. So once you found such a node, you join that node X with one of its neighboring nodes and replace those individual nodes X and Y by a joint node X join Y. Yeah, and then you loop again. So you can still check has the cycle, until you find out that it is acyclic. Once it's acyclic, you can run the Yannakakis/Bernstein algorithm, pick a node from G as root. Again, that leads to the root node enumeration problem. Depending on which node you pick as the root, you may have different costs that may take different time. Yeah? So it's a separate problem. Then you perform Yannakakis, which means bottom-up semi-join reduction, top-down semi-join reduction, and then you're good to go. Yeah? Then the result of that, you're almost there, except now you have to clean up the mess you did in phase 1. Because if you have nodes that are join results, now you have to project them back to the individual relations. Yeah? If your graph in step 2, if your graph you put in already is acyclic, each individual node represents a single relation. But if you joined to get rid of the cycles in the graph, you may have nodes that represent join results, and then you have to do something similar to what we did in the rewrites. You have to project to the individual relations to split them up again. And then you return the database. Okay, and again, by returning the reduced database, you could actually feed that into standard query processing. So it turns out when you do experiments on that, if you first run this stuff and do standard query processing, in many cases it doesn't pay off, but there are cases where it actually pays off. And it's ongoing research to find out whether this Yannakakis algorithm can be applied. Okay, so conclusion for this part of the lecture is really a shoehorning SQL and the beauty, simplicity, and expressiveness and the power of entity relationship modeling into a single result table leads to many, many problems. I showed 8 of those problems. And all of these problems are artificial. So that's what I meant before. So you introduce a constraint. You say, okay, my SQL result returns a single table. And that introduces artificial problems, which is cool for research because then you can work on artificial problems and can write my own papers. That's awesome. Yeah? So we sometimes do that. But actually, if you think about that, if we didn't have that constraint in the first place, all of these problems would disappear all of a sudden. And that's super cool. Yeah? When you just say, OK, I don't need that constraint. It can be as many tables as you want. Yeah? So if you allow SQL to return a subdatabase, all these problems are solved. We have ongoing work because if you think about that, it has many implications on query optimization and query processing. And again, last time someone said it's just an interface. Yeah, I'm planning to make a T-shirt with that actually. So what I changed in the interface was just the return type rather than returning an iterator of objects. I said no, the return type is now a subdatabase. Maybe this is, how many characters is that I write in my program? It's 10, 15 characters. But the implications, it's like an avalanche through the entire stack. Yeah? Everything is affected in the database. And that makes it really cool. Yeah? Many things can now be revisited and re-researched, so to say. OK, of course, we have a notebook on that. Where's my notebook? Here's my notebook. So we have the query like that. We have slightly different from what I had on the slides. So it's not about professors giving lectures. It's persons ordering books. So we have persons. We have persons and books and orders. Yeah, it's an end-to-end relationship, of course. Every person can order every book. And which person orders which book is represented in this through table in the middle, this orders relation. We will be using DuckDB. Ever heard of DuckDB? Yeah, so that's kind of, I'm not want to say replacement. So the most popular database, embedded database, yeah, that is used as library is SQLite. It has trillions of installations. Actually, last summer we had Richard Hibbs here giving a talk. He's a co-inventor of SQLite. It was a super great talk. That's still on YouTube on my channel. I highly recommend you watch it. It's an awesome talk. Very interesting to see how SQLite is doing that. And SQLite has a certain focus on OLTP, on transaction processing in an embedded scenario. Yeah? You have SQLite on your phones. I don't know how many installations, mail programs use this stuff on each of your phones. Yeah? However, when it comes to handling larger data sets, when your focus is more like analytics, and analytics typically implies that you don't have transactions, you don't care about transactions. The database is not part of a Django, whatever web application, it's just you have some data, you want to analyze it. For this, you have OLAP, online analytical processing databases, and DuckDB is in that space. So DuckDB can also support transactions, but they really optimize it for analytical. Yeah? And it's a great system developed in the Netherlands by CWI and the spin-offs and stuff. Yeah? Really cool system, also fancy SQL extensions. Maybe we look at some of the SQL extensions also as part of this lecture, because I really love the stuff. And it's a great system. Yeah? And we're using it, and that's your all the installation you ever have to do. Import DuckDB, and then now we have DuckDB. Okay, so we create some fake data, person, book, and order. So we created some data classes for that. And basically then you have a Python data class again. This is key value pair, so persons, 3 persons with name, Alexandra Fitzgerald, birthday, and so forth. Then we have certain books. And we have orders, so person ordering that book. Yeah, and now what we do is we can do a semi-join plan based on that. And we use relational algebra for that. So basically we wrap each of the inputs into a relation, yeah? Basically like on the slide. So we have a relation for persons, one for orders, and one for books. Okay, we want to filter. We only want to have those books where the price is strictly smaller 10. So basically, okay, we say that's our input relation. We use another operator that's called the filter, and we receive the filtered books. Then we perform a join. Yeah? In this case, it's a simple hash join. We had that briefly in the undergrad lecture, basically using a hash table to join the results. Doesn't matter how that is done internally for the moment. It's a join, joining those 2 inputs, rel orders and filter books, and those are the join attributes to use. So book title is the attribute from rel orders, and title is the attribute from filter books, and that's an equi-join, returning only the matching results. Then we have filtered persons, which is a semi-join on rel persons and join orders. Again, you have to specify the join condition, and then we get the query plan like that. So this is a query plan as you would also see it from a database system if you write explain plan. Yeah? You can do it on the command line. If you write SQL in a database system, you can always prefix that with explain plan or explain analyze. Or if you use a visual tool, there's some button somewhere hidden where you can get an explanation or profiling or something like that. You get a visual representation. But this is a textual representation. It's basically saying the nesting represents the inputs. Yeah? So relation books is an input to operator filter. Then this simple hash join has 2 inputs. One is the relation orders, and the other is filter. Then again, on a level above, the semi-join has 2 inputs. One is the relation persons, and the other is a simple hash join subtree in a way. Yeah? So if you write this as a tree, you could say print. What's next? Semi-join. Semi-join has 2 inputs, persons and simple hash join. Persons and simple hash join. The simple hash join has 2 inputs on the left orders, and then the filter orders. Then the filter on books. So that's a selection, price, smaller 10, oops, books. Okay, so that's the standard relational plan, basically just spelled out as some text. Yeah, and that's typically also what you get from systems when you do explain plan. Okay, so this is returning the, so how do we read the queries? So this is now returning, so if you look at the joins, so this would return all persons joined with orders and books where the price is smaller 10. So basically I want to have I want to have all persons that ordered a book, that ordered a cheap book at some point. It's basically the semantic of the query. Yeah. And that's what I'm doing here and expressing here as a semi-join. Yeah. And this is again very similar to what we had on the slide. Maybe I can show it again on. Where's our rewrites? Here, this one. Right. Yeah, this is basically here. Here, where difficulty is low, and here this condition L.id in, or here it's overwritten with all the scribbling in. Yeah, in. Meaning it is contained in that, it exists in that join. So the problem here is that SQL doesn't have an explicit semi-join. You can't write it in SQL, it just doesn't exist. So there are two ways how to emulate these things. One is via distinct and the other is via a subquery. And that's why you see that in these rewrites here. Okay, so now we use a little bigger example here. So we created some, we want to create some bigger data here and look at the different rewrite methods. Yeah? And we basically now create a DuckDB database in memory. You can also materialize it. We will put it to this, but we don't have to do that. So we send some create table statements here. We convert the data we had in lists above to data frames. Data frame is Pandas data frame is a popular library in data science. I don't like it because it has a very bad API. I like interfaces, you know, and then data frames are just really, really bad. But it's useful because it's integrated into so many libraries, and that's why we're using it here. Yeah, and then what we do is basically we replay the stuff I showed you on the slide. So this is a dynamic select distinct version. So basically I send a select distinct persons. For each relation I send the original query, and on top I do a select distinct on persons.star. So all attributes that exist for this relation, and by that I get a result database. So each of these iterators gives me the result I want to have. So this is the result database I was talking about in the slides. This is for persons, this is for orders, and that is for books. Same with materialization, now live in a notebook. DuckDB does not have a create materialized view, so you will see that with many database systems. You can't write create materialized view. In Postgres you can write it, I think in Oracle you can write it, and DuckDB you can't. Probably for historic reasons. My general recommendation is don't use it. Don't use materialized views. This is more like for didactics and explaining you the rationale behind ResultDB, but for development, yeah, for retrieving queries, for executing queries in database system, you should never ever use materialized view. Don't do it. I would claim that 99% of the problems you can do with materialized views can be solved in better ways. Materialized views lead to update problems and all kinds of fluff, and this is basically a technology that was invented in the 90s to handle performance problems. Back then, database systems ran on disks with platters, with spinning platters. I/O was super slow, and people had really, really big problems with certain queries. This is not true anymore. Yeah? So it has to be a really insane query on insane data that you need materialized views. Or ResultDB. Okay, but you can really solve ResultDB differently. It's just for the purpose of showing how you could do it in principle. And performance-wise, it doesn't hurt you anyway for this toy data. Yeah, so, but that's what I showed here. Basically, you first materialize the result, and then you select stuff here individually. Ah, this is fantastic. How many problems does this cell have? Shall we count? Same as before, obviously. No transaction, right? Yeah, if anyone kicks in between, I do the select and someone else does the select. Is that a problem? Yeah? Yes, exactly. So slightly different from what we had before. Yeah, there I wrapped it, selecting and executing the query dynamically for each and every relation. So that could be a problem if in between someone updates any of the relations. Here, this materialized view is a snapshot. It's a snapshot I took when creating that. Yeah, the same as an MVCC, a snapshot, a version of the data as of the time when I execute this statement. Yeah, then I take the current version of whatever those relations are at that point in time, put the join result into this new table, and then I query it. So this is not a problem. Querying is not a problem as long as no one in between those queries fiddles with this table I'm creating here. That's fine. Yeah? But still there's room for these problems. Yeah? So what does it mean for the snapshot created by the materialized view versus the snapshot I have in MVCC? And why do I ask that? That should have been an exam question, right? Yeah?
So the snapshot created by materialized will stay on their physical things. And,
stay on?
On the hardware.
Yeah, sure, it's stored somewhere and it must be persisted. It's asset property, so database system has to guarantee that it's not lost, yeah? Mm-hmm.
And the snapshot from MVCC doesn't stay on the hardware.
Naja, but it's also, you have asset properties for MVCC, right? So whenever someone writes, if you don't commit, I don't care. But if a transaction commits, you must make sure that whatever you changed must be persisted, right? It's just the parts that are never committed or just represent some sort of intermediate state in a transaction. I don't care about durability. But once you commit, you must make sure that everything you change in your snapshot must still be persisted. Yeah? Yeah?
So basically this snapshot is only for reading. We cannot commit and you never change it. But also the problem with this is we do not necessarily guarantee that it will be modified. Like basically if there was another table that worked on a similar table named materialized view,
Yeah.
it could be modified in between. And
What do you mean by similar? Not.
at the same time, there was another query that also wanted to work on a table called materialized view.
Yeah.
We would have a conflict because we just have one table called materialized view.
That's a read-read. It's no problem. Yeah? So that's not a conflict. So if the other could actually reuse it. The problem is only if you try to create it with the same name.
Yes, and
Yeah.
the name conflict is
Yes.
like there will be other query that would want to use a materialized view,
Yeah.
and if we try to create a table with similar name,
Yes.
we need to basically ensure that the names are unique.
Yeah, right. That's a good point. So the naming is really shitty. A materialized view database system has many other users. Yeah, it's high potential for conflicts. That's true. Yeah. What other problems do you see?
It doesn't get removed after.
Yeah, right. I mean,
That will be removable, but
yeah, I would clean up, right? Drop table afterwards would help a lot because maybe I just use it. It's kind of a temporary table I'm creating here. I better remove it afterwards. Good idea. Yeah. What else? Wrapping into transaction. General problem with materialized view is anyone touches any of the base relations with a write operation, the materialized view is outdated. Yeah, and then you get again into conflicting, the potential to create conflicts in a way. Now you do some changes. I mean, this is just again, this is just read only. Yeah, if you say this is a temporary table, you drop it anyway. So basically, you don't write back to the actual relations in this statement. Yeah? So it's kind of a read-only transaction if you wrap it in a transaction, because this is just selecting. But assume based on this result database, again, now you do a change. Yeah? And maybe there's a outdated version in your materialized view. Yeah? Then you are in conflict land. Yeah? Good luck with that one. Yeah? Good. Then we also have the native algorithm here to compute a result database. That's what I explained on the slides. You choose an arbitrary node in the join graph as the root, perform bottom-up semi-joins from leaves to root, perform top-down semi-joins from root to leaves. These two passes, compute the final join result by adjoining the reduced relations. That's what we do here. So we have implementations of the individual operations. This implementation is list-based. So for filter, for instance, you get a relation, you get a predicate expressed as a string using eval. Eval is evil. Don't do this. Injection security, don't. No, don't. You didn't see this, okay? It's just a notebook for the lecture. Yeah, you don't use this. We may make a comment. So here you execute that on the global context, and then basically it's the same as writing the predicate explicit. It's not the same. It's in a string you have your predicate, and then you evaluate that and append the results. When a tuple qualifies, you append it to the result list. That's a simple filter looping over the input data. Then we have the semi-join. Maybe we look at that briefly, how that is implemented. Left relation, right relation, both as lists. Why is that a dictionary? In this notebook, the idea is each tuple is a dictionary. Yeah? Key value, name, value, Fitzgerald, birthday, whatever. Yeah? Each tuple is a dictionary, or you could model it as a dictionary if you want. And that's how this implementation does that. Then there's a left attribute, and that's the right attribute. These two basically represent the join predicate of that join. Semi-join also has a join predicate. And this computes the left semi-join between the given relations, which means the left input is filtered and reduced. So this function answers, okay, if I joined the left relation with the right relation, which input tuples from the left relation would be part of that? So basically, I'm reducing the left input relation in the algorithm. How does that work? Again, it's list-based. So disclaimer here is real implementations would do this stream-based. So database systems also always try to avoid buffering intermediate data. We will look at that later in this lecture. There are many great tricks you can play. This is just to make your life a bit simpler. But the real implementation would have iterators and streams and whatnot. But this makes it more readable. So we have a list of output tuples, aka dictionaries. We built a hash set in this this idea. Okay, because you just have it's already a bit of a trick. So you don't need the only thing that you need to hash here is the join attribute of the right relation. So basically, you want to know from the right input, and there the join attribute as part of the predicate, which do exist. Yeah, you basically build a set. That's what this is doing. You add the right attribute of the join condition. The join predicate is left attribute equals right attribute. And now what I'm doing here is I take all the tuples from the right relation, project them to their right attribute, and whatever that value is, I add it to the set. And the set removes all duplicates. So after executing these two lines, I know, my set only contains those tuples, only contains the keys that occur in the right relation. Yeah? Is that? No? Explain again, or? Who is in favor of explaining it again? Okay, explain it again. So maybe I need the board again. So we're doing a left semi-join. This symbol. And the input is left relation, right relation. I call it L and R, okay? L and R. And there's a join condition. Left attribute, right attribute. Let's call it L equals R, where L is from relation capital L and small r is from relation capital R. So the first thing I'm doing in this line here is I create a unique set of the R attributes, of the R attribute values. So for instance, if my R relation has whatever, attributes 1, 2, 3, 4, something like that, the set will have something like 1, 2, 3, 4. Yeah? The unique attribute values I find in this particular relation. Yeah, it's basically like in relational algebra, it's equivalent to projecting to this attribute. Relational algebra removes duplicates, already done. Yeah? So as I don't have relational algebra here, as I'm operating on lists, and potentially two tuples in the right relation may have the same attribute value in that right attribute, I have to do something to get rid of duplicates. And that's what I do by using a set. That's my hash table. Yeah? So internally, it uses hashing to do that. So the post condition after these two lines is, okay, now I have a set with the keys that occur in the right relation. I want to reduce L. I want to have those tuples that take part in a join with R. So what can I do? Now I loop over the left relation, and for each tuple, I check whether its left attribute, so here on the board, it's L, occurs in the set. Only if that is the case, there is a join partner for that tuple in the other relation. Yeah? If it's not, if any tuple from L, let's say whatever, 42, yeah, and the L attribute, let's say that's the L attribute, and you see, now you have this tuple in your hand, currently, how do I call it, tup is whatever. Yeah, and now you look up, okay, is 42 contained here? It's not contained. That implies this cannot be part of the join. So if you joined L with R with a standard join, yeah, this tuple would never take part in the join result, yeah, because it's not 42 is not contained in the set. Yeah? So basically, that's what you are answering here. And did you ever bump into yield in Python iterators, implemented Python? Yeah, if not, maybe look it up, yield. So this is a great opportunity to use yield. Yeah? So rather than having here this materializing everything into a tuple, a better way of doing that here would actually be to call yield tup. Yeah, and by that you could define this function as an iterator. And like that it would produce these tuples only on demand. So but that's a Python feature. Eh? So if you've never used iterators, maybe you want to read that up. It's really, really handy and useful. So this is an implementation of the semi-join, left semi-join. How would you implement the right semi-join?
Basically do it the other way around. So
Yeah.
build a hash set on the left relation and then poke in all the tuples from the right relation.
Yeah, correct. Other proposal?
Just call the exact same function as well.
Yes. Lazy. Be lazy. Really important. Laziness principle, computer science. Besides that in the undergrad lecture. The same thing. Yeah, you don't have to implement it, so you could do the same, just inverting it. Huh? But you're also right, you could also have a separate function on that, or you have a function rerouting to this function, inverting the inputs. Yeah? That's the other way. Yeah, okay. And then basically what the notebook does is, yeah, it computes join orders. Basically, by picking, you can pick a node, and then based on that node, it computes its semi-join orders and performs the actual semi-join reduction here in that notebook. Maybe I should have executed the cell. Restart the kernel. I know here I can do that, right? All right. Here we go. Yeah, and then you see, okay, that's the state of those relations before the reduction, so the full-blown relations, and that's the state of the relations after the reduction, and so forth. So yeah, we don't, also we have a generator, we should actually put that into a list, yeah. Forgot to put that into a list. Yeah, the Yannakakis algorithm, you see here, that's again, as on the slide, so here we choose an arbitrary root node. Again, that should actually be part of cost-based optimization. We perform the semi-joins, semi-join order and the semi-join reduction. And then we perform the joins to obtain the actual result. Yeah? So this returns as single, why is the output 0 now? So it could only mean there's no result set here, not sure. Not sure what happened in this one. Maybe my refactoring this morning killed it, not sure. Yeah, need to take a look at that afterwards and why that is broken, or why it could be broken. But the main bottom line, that's also what you see in the code here. If you look at this result TB I presented, so it's very similar to what we do in this Yannakakis method, except we don't do the third part. So once we obtain the subdatabase, we stop. Yeah, that's what we return. In SQL, if you operate with standard SQL, returning a single result table, you still have to join it. You still have to do standard query processing. Ideally, calling a query optimizer, coming up with a decent query plan. So we do that manually here in this example, yeah, by putting together individual operators into a plan. But that's the job of the query optimizer, actually. But basically, the analogy here is that we just do the Yannakakis algorithm in the sense that we do a subset. Just we pick a random node, we do bottom-up, top-down, semi-join reduction, and then we're good to go with this example. Okay. Oh, my unit tests fail. How the heck is that possible? Maybe I want to restart the kernel. Ah, yeah, of course. Yield, right. Awesome. I didn't remove it. Oh, yeah. I should. Oh, sorry. Okay. Yeah. Oopsie. And that makes sense, the error message that there's a generator where there is actually no generator, right? Ah, here, okay. Nice, okay, now I have the state, okay, now I also have the reduced tuples and not only a generator. Very good, excellent, yeah. And then this makes sense. Yeah. Okay, so I suggest you take a look at that. I don't have to take a look at that anymore as my tests seem to pass. Awesome. Right. And that's basically all I wanted to tell you about ResultDB. Good. With that, we will now enter, look back at our store actually. And what we will be looking at next is how to create indexes in our store.